So, which one was it? Given the force versus displacement graph below for a net force applied horizontally to an object of mass m, initially at rest on a frictionless surface. Determine the object's final speed in terms of fx, r1, r2, r3. Okay, so what does force versus displacement graph tells you?
Like the work, basically.
That's right, that's the work. So, once again, final speed. It should be here.
And I think we didn't complete the last section.
Sorry?
We didn't complete the last.
Yeah, we're going to do it today. Right, okay, so now let's find the work.
Okay.
Shall I do it on the board?
Yes, please.
Given the force versus displacement graph below for a net force applied horizontally to an object of mass m, initially at rest on frictionless surface. So it had been initially at rest, and after a certain time it has gone a certain distance, that it has gone up to r3, by which it has acquired, let's assume, v velocity. Okay? So whatever the work he done is, we know that it's energy and is converted into what kind of energy? Is converted into what kind of energy? Yeah, kinetic energy. So work done is equals to kinetic energy. Learn the concept. First get the concept, then it's easy. So kinetic energy can be, initially it was at rest, so it did not have any kinetic energy at the beginning. So it was horizontal, that means there's no potential energy as well. Okay, so half mv squared is whatever the work done. So the work done has to be calculated from this graph. Okay, so the area of the force versus displacement graphs give you the work. So what shape, what is this shape?
Trapezoid?
Yes, trapezoid. So how do you find the area of a trapezoid?
Base 1 plus base 2.
Yes, area of graph. I'll write it like that.
So
this distance plus this distance divided by 2, the average of these two distances, into the perpendicular height. Okay, so what is this distance? That's R2 negative R1.
Yeah.
Got it? R2 negative R1 plus. We need
R3.
this one, so that's straight away R3. And the average of it. And what do you get? What do you get next? F max. So F max, let's keep it as F. So half mv squared. So we want v squared. So what should we do next? Yes, this 2 is common for both sides. Let's get rid of it. So it's v squared. Take this m towards the other side. Then this becomes f over m r2 plus r3 negative r1. So, okay, I'll do the next step too. Square root of the entire thing. R2 plus R3 negative R1. Got it?
Can you just leave it like that?
Yeah,
No.
yes, that's how it is. When you have symbols, when you have signs, you must simplify it in the most simplest form as possible. Okay? Alright. So, they will take your packet out and see whether you have done any mistakes in the questions that you did at home.
Okay.
Right? And if there's any, if you have any trouble with any questions, if you have done anything wrong, we will discuss it at the end. Okay? Alright, now we'll go to the end, the last one. The very last one was conservation of angular momentum. Conservation of angular momentum. So, what is sorry, not angular momentum. We are going to do it today, so sorry for that. Momentum, conservation of angular momentum. What do you mean by conservation?
Like
Conservation.
saving.
Oh, yes. Conservation of energy. Energy is conserved. Energy is constant. Similarly, conservation of momentum means momentum is conserved. But there are certain terms that you have to remember. Okay, I'll tell you what it is. Conservation of momentum. If you represent the conservation of momentum, momentum is a vector. Therefore, you should indicate the direction. So, in a certain direction, in a given direction, the in a given direction, the momentum of a certain system is conserved in a given direction. And if there are no external forces applied on it, the momentum of the system is conserved. Do you understand?
Mm-hmm.
So you should remember the word direction and if there are no external forces applied on the system. Okay, so I think that's, is it given in your text? No, yes, okay, write it like this. Momentum in an isolated system is conserved. So what do you mean by isolated? Isolated means,
Okay.
yeah, nobody is interfering in that person or that system. So that term is already there. What I mean by not, that it is not being interacted with any other forces. Alright, so let's take an example. Assume we have two wagons or two cars. Let's call this A, let's call this B, and let's assume that the mass of this is MA and the mass of this is MB. Okay? And let's assume initially the velocity of this was VA, yes, and this was VB, and they were moving in the same direction. And if VA is greater than VB, so obviously A would hit B. So after a certain time, let's assume that they collided one another. And what do you think that their velocities would be? Let's assume, now still this is MA, this is MB, and let's assume that their new velocities are VA dash, VB dash.
V would be slower than V.
Yes, we don't know. It depends on the masses and the initial velocities. So it can be greater, it can be more, it can be less, sometimes it can be in the opposite direction. It depends on the magnitude of the variables that we are writing. But this is the common scenario that I'm talking of. So I say, in conservation of momentum, you need to take a direction. So, all the trolleys or all the vehicles are moving in the forward direction, so I'm taking this direction. So whenever you do a sum, you should write these terms. Using conservation of momentum, what is the momentum of this? Momentum of this plus this is equal to the momentum of this plus this. That's the base. So momentum of the first vehicle is MAVA plus MB VB, and please remember, okay, I'll talk about it next. MB VB should be equals to MA VA dash plus MB VB dash. So depending on the magnitudes of these variables, your sum will be either to find the final velocity of the wagon B or final velocity of wagon A or whatever it is. Okay, so this is the base. If there were, okay, can you write this down?
Yeah.
Quickly draw this down, sir. Take 1 minute. Alright, okay. Now I'm going to do some alteration onto the same diagram. I'm going to change the direction of my second wagon. And let's assume that both of them are moving in the same direction. Okay, let's assume. It can be the other way. So now, what would you get? It would be MAVA for the first one. It won't change because the direction is in the same direction. Now, what's happening to the sign? It should be negative. That's right, minus. And this one, okay, let's change it. Let's assume they are changing. Okay. So what should this be? This should be negative and this should be positive as last time. Alright. So when we replace these values with their numerical values, sometimes even if you use a negative sign here, you may get like now we wrote this formula using the negative value, assuming that this is moving in the backward direction. But even if you wrote it like that, and if you get a negative numerical value like negative 10, what does that mean? That it is not moving backwards as we thought, but it is moving forward. Okay? So please be careful when you use the signs. Even if you draw the wrong direction, ultimately you will find the correct answer. Remember that. Alright? Okay, so would you quickly do the second one as well? Draw some balls, don't draw wagons. Okay, so last time I said change of momentum. The change of momentum can occur due to two reasons. One, mainly due to a change in velocity and a change in mass too. So I was talking about an explosion, didn't I? I told you that if there's an explosion and if the particle breaks into two, then that two is considered as a collision, and that too can change the momentum. Okay, so let's consider that there was a bomb like this. Assume that this was a bomb and it exploded into two different particles. Let's assume that this was 2m and this is m and this is m. Let's assume that it broke into exact two halves. Alright? Assume that this was initially moving in the forward direction, and upon explosion this one moved this way and this one moved this way. And let's assume that both angles were the same, that they exploded into in same angles to two opposite directions. Right, now how do you use the conservation of momentum to this? Now once again you have to consider the direction. Now do you say in the same direction? In earlier example it was just one direction, either forward or backwards. Now you see three directions, don't you? You see a forward direction, then you see movement upwards as well as downwards. So in these cases what we do is we consider two directions, two perpendicular directions, either this way or that way. So you can write using the conservation of momentum in this direction. Initially, what was the momentum? 2mv. Now what is the final momentum? M. Let's take particle A. Let's take particle A. Can you remember the resolutions I talked about last time? Like when there was a force like this, would the magnitude of the force be the same in this direction?
No.
No. So what would it be?
Like
It should be F cos theta. Do you remember that? So in the same way, now you must take the horizontal component of the velocity of this particle,
Right.
not this velocity. If you take this velocity, then you are wrong. So it should be mv1. What should it be? Is it cos theta or sin theta? You are closing. Therefore, it should be mv1 cos theta. Okay, and what about this one?
MB.
Plus
M.
don't call. Okay, let's call it MAMB. V2.
Sine.
No. Still, we are considering the forward direction, so it's downwards. So its horizontal component will be in the forward direction. Do you understand that?
Okay.
Okay. So MB V2 cos theta. So this is the final. Whatever you do with the numerical values, this is your equation. But this is not it. You must consider the perpendicular direction too, because there are too many variables. For that case, what would be the initial momentum? What would be the initial momentum for this case, for the perpendicular direction?
This, the same thing,
No, y is not.
different directions. So
Yeah, it's v is in the forward direction, but
And
we are
negative?
considering not even negative. It's the perpendicular direction. So it's exactly. If you take the resolution, it should be v cos 90. V cos 90 means 0.
Okay.
Therefore, it's 0.
Okay.
Okay. So you see that there is no velocity in this direction. Do you understand that? So initial momentum is 0. Now what would happen to this? This is MA V1 sin theta.
Is this going?
Now, what should this be? What should the sign of this be? When you close it this way, this is the perpendicular direction. When you
So
close
we-
it this way, it's negative.
Yeah.
So it should be negative MB
Because it's going opposite
V2.
direction.
That's right, sin theta. Got it? Okay? Yeah. Okay, quickly write it down. If you don't have space, you can go to the next page because I have already done these steps.
This page?
Yes.
Okay.
Create a momentum table where, yeah, draw it here because I have already done this.
Okay.
Okay, so while you draw, listen to me once again. When you get a when you get a collision, what should you use? You should use conservation of momentum. First of all, draw the figures. Draw the figures before the collision and after the collision. Mark their masses and the velocities in the given directions according to the question. Then take conservation of, if they are in angles, take conservation of momentum in two perpendicular directions or take it in the same direction. And write M1 V1 plus M2 V2 equals M1 V3 plus it's like this. M1 V1 plus M2 V2 equals M1 V3 plus M2 V3. Got it? Understand? Okay? So it's not difficult. Alright. We're done. Shall I erase this?
Yeah, yeah.
Okay. Okay, now go to the next sum. A 200 kg car traveling at 20 ms minus 1 collides with a 1000 kg car at rest at a stop sign. If the 2000 kg car has a velocity of 6.67 after the collision, find the velocity of the 1000 kg car after the collision. Okay. Draw the figure before, after. Before, after. That's the best way.
Where is it?
Make
2000?
it 200. No, yeah. Yes, make it 2000. Yeah.
So,
Make it yes, make it 2000. So you draw the car first. This is the car. So this was moving at a velocity of 20 ms minus 1. This was 2000 kg and collided with another truck or car or whatever it is of 1000 kg,
it's at rest.
which was at rest, so u equals 0. Now draw the next scenario. If the 2000 kg car has a velocity of 6.67 after the collision, find the velocity of the second car. Okay, so you assume a direction. So do you think that this would move backwards? No, it's common sense. Even if you can't use the common sense, because if you have two cars which are moving in opposite directions and if you have no idea as to what's happening, what's going to happen next, then you can use any direction, no harm. Okay, so let's mark it forward. Okay, now what should you do? Did you write the first equation?
Yes.
So it should be 2000 into 20 plus 0 equals 2000 into 6.67 plus 1000 V. Okay, so at a glance you can get rid of these three zeros. Try to simplify as much as possible. Okay, so this should be 40 equals 2 into 6.67 plus V. So V is 40 minus whatever it is. Do you understand that? So it should be 12, 13 something. 2 into 4 is 14, 13, 13.34. So it should be 6, 6. I hope I'm correct. And this will be 6.
Negative 667.
It is not negative 667, is it?
No.
Can you check that please, because that's very important. So it should be 26 plus 66 ms minus 1. Did you get it?
Yeah, I messed up the first time.
Because in this case there's no way the velocity of the 1000 kg car
Can we go back?
can go back. Okay, so the next sum you can do at home. Alright, so the next, go to the next figure. It shows a diagram which stick to one another upon collision. So write an expression to describe the final velocity of the masses after the collision in terms of MA, MB and VO. Can you do that please? Let's take 1 minute to do that. Now both of them move as one. Both of them move as one. So it should be MA, VO, what about MA, VO.
Oh, okay.
Momentum of this plus momentum of this is equals to the momentum of the whole thing. Once again. No, Siddharth. Momentum of this plus momentum of this is equals to the momentum of the whole thing. MA VO plus MB, that's right. This was at rest. Was this at rest initially?
Yes, at rest. So they doesn't have velocity.
Yeah, that doesn't have any velocity.
So it'd be
Yeah.
How do I do it as one figure?
So make this 0. Yeah, okay. So what would be the mass of this when they stick to one another?
MA plus
MA
MB.
plus MB, right? MA plus B. And that is MA plus MB. MA is one, MB is the other. So this is the entire mass now.
Oh, and then
Okay, that one into,
Yes.
that's right. Got it?
Yeah.
Yeah. So what should you find now? You should be able to find the final velocity, that is VF. Okay, now what should you do?
We can divide.
Yeah, now this becomes 0.
Yeah.
Yes. Do the next step.
So M
A
A
V O
plus
equals because this becomes 0. That's right.
M
Plus
Plus
MB into VS. Okay, so now you need to isolate VS. What should you
A.
do?
Divide by MA.
Divide. Yeah, that's right. So can you write the final answer? MA VO over MA plus. That's right. Did you get it?
Yeah.
Yeah. So you did one mistake while you were writing. I saw that you wrote MA plus B. That's wrong. MA plus MB.
Okay.
You wrote a plus B here.
Yeah.
That's wrong. Be careful. Okay. Now did you get it? All right. Okay. Next sum 2 I'm going to do because we are talking about a recoil velocity. Do you know what the recoil velocity is?
Like
Yeah.
Is it
When you
backwards?
shoot. Yeah. When you shoot. Suppose you have a heavy gun. And of course we have. Both of us have not shooted. Has not done any shooting before. So what have you seen in movies? When
They
you
go
shoot,
backwards.
you go backwards, right? Well, why do you think that backward velocity comes from?
the momentum
From
of
the
bullet.
momentum. That's right. From the momentum of the bullet. From the momentum of the bullet. That is from the product of the mass of the bullet and the velocity. Of course, the mass of the bullet is extremely small, but we know the bullet is extremely fast. Therefore, it has a considerable momentum. That's why. Okay, now let's see what's happening really. Let's do this sum, then you will understand what's happening. A 4 kg rifle, this is the rifle, okay, fires a 20 gram, this is the bullet. So this is a 20 gram with a velocity of 1500 ms minus 1. So imagine the velocity. So it's even though this is extremely small, the momentum is extremely large because the bullet is fired in an extremely high velocity. So find the recoil velocity of the rifle. So what's happening?
It's going
So
backwards.
this is going backwards. Let's assume that it was V. And what was the mass of the rifle? 40 kg. Alright, now this is a collision. You don't see, even though you don't see a collision, this is an explosion. So what is an explosion? An explosion means ultimately you have a change in momentum. Do you understand that?
Yeah.
So now do you understand how to use the momentum?
Yeah.
That's what most kids get confused of.
Okay.
Okay, so now using conservation, I will write this in short, conservation of momentum in the forward direction. Now tell me, what is the momentum initially? What was the momentum initially?
1500.
Huh?
15.
What are the two objects?
The
The
bullet,
bullet and the rifle. Were they moving?
No.
They were not
So zero.
moving. So initially, the momentum of both objects was
Zero.
0. 0 plus 0 equals. Now let's write the bullet. It's in grams, so let's convert it into kilograms straight away. 20. How do you convert it into kilograms?
Times 1,000.
Yes, 10 to the power.
Yeah.
10 to the power minus 3. You have to divide it by 1000, so it
Okay.
should be 10 to the power minus 3. Get used to that straight away.
Okay.
Don't divide it by 1000, but write 10 to the power minus 3. Into that's mass and its velocity is 1500. Then what happens to the next? Should it be positive or negative?
Negative.
Negative, that's right. 40 V. So you will get 20 into 10 to the power minus 3500 equals 40 V. You can get rid of this 0, and remember, you have 1, 2 zeros, and that when you cancel that with this negative 3, it becomes negative 1. So 2 into 15 is 30. 30 into 10 to the power minus 1 divided by 4. So this will be 15, 7.5. Yes, 15, 7.5 into 10 to the power minus 1, if my calculation is correct.
Yeah, that's right.
So 0.75 and as minus 1. That's why most rifles, cannons and all weapons are made heavy. That's why they are made heavy. So the that, the recoil velocity will be as small as possible, and the gunman is not being forced back. Okay? Alright, so I want you to do the next sum. That's a little bit, I want you to try the next one because I'm running out of time and I have to start the next lesson today as well.
Which one?
There are two more sums.
Okay.
Yeah, there are two more sums. And if you don't understand, I think you will get confused with the sum. Please ask me next time.
Okay.
Please make it a point to ask me the question next time. Okay? Alright, now I'm planning to go to the today's lesson. So today's lesson we'll be doing about rotational motion. So on the first lesson we did about linear motion, or I said we also call it rectilinear motion or translational motion. There are so many words. But you are not here. But you already know that what velocity means. What is velocity?
Speed.
Displacement over time. And what is acceleration?
Speeding up.
So we are actually not considering speed at the moment. We'll be considering velocity, the vector form. Speed is not the not in the vector form. So let's call velocity change in velocity over time, or you can also call this one as rate of change of displacement, rate of change of velocity, and these were the two terms that we talked about last time. Okay, now we are going to talk about the same aspects if a particle is moving in a circular motion. We call it rotational motion. All right. So yes, okay. Let's consider. So I think the note is given. You don't have to write anything. If this is a particle, and if this is a center, so if a certain particle is moving in a circular motion, it will be moving around a certain axis. So if this is the axis and if this is the particle, and if it was at this place at a certain time and it was at this place at another time, then this theta marks the angular displacement. So what is this what is meant by theta? Angular displacement. That is the angle the particle sweeps during a given time. Understand? Okay. So if this length is s, if the length of this arc is s and the radius of the circle is r, do you know how to write a relationship between s and r and theta? Do you know that? S equals r theta. So if you have an arc, You should have done this. You may not remember. You should have done this in math. So if the length of this arc is S, and that angle that it forms at the center is theta, which is bound by radius r, S can be written as r theta. Do you understand that? Alright. Now I'm coming to angular angular, yes. Okay, so I introduce the word angular displacement. So angular velocity is equals to change of theta over change of time, displacement over time. Keeping this in mind, let's go back to this one again. S equals r theta. I'm going to divide both sides by t. If I divide one side by t, I have to divide the other side by t too, because it's not going to be fair otherwise. So if I divide this side by t and this side also by t, then what do I get? What is S over t?
Speed over time.
Displacement over time. What does that mean?
That's
Velocity, the linear velocity. Do you understand?
Mm-hmm.
And what is, if I erase this part, what would this be? Angular velocity. Do you understand that? S equals r omega. So I forgot to tell you that we denote the angular velocity using omega. The Greek omega is a letter in the Greek alphabet. So it's actually not W, it's like this. Okay? This is omega. So V equals R omega. So velocity is always V, radius is always R, angular velocity is always omega. So if you see an omega, that has to do with an angular velocity. Okay, so this is the relationship between V and omega. Okay, so if this was the particle and if V was the instantaneous velocity of that particle at a certain time, even though it's moving circularly, at a particular given time, it has a linear velocity. Do you understand that? So if that linear velocity is V and the angular velocity is omega, then the relationship between V and omega is always V equals R omega. You understand that now? Alright. Now, so do you have that in your note?
Yes.
Yeah, so you can bracket, you can block this up. Alright. Now I'm going to go further. Now once again I'm going to V equals R omega, and I'm going to introduce you the next term, the angular acceleration. The angular acceleration equals, what would that be? Change in velocity over time. Okay, to the same equation, now I'm going to divide the same equation by t once again as I did before. Do you understand? So V over t would be, what would V over t be?
Acceleration.
Yes, linear acceleration. You don't have to say linear. I just stressed that, even though I stressed that. So A equals R. What do you think that omega over t would be? That's the rate of change of angular velocity. What does that mean? That's the angular acceleration. And that's always denoted by alpha. Do you understand that? So VA equals R alpha. Now do you see a certain relationship? Do you see a certain relationship? S equals R theta, V equals R omega, A equals R alpha. Do you understand that? Okay. So always the linear component is equals to the radius into the angular component. Right. Now S theta V omega A alpha, all of these are vectors. Now can you tell me what the direction of omega and alpha would be? what would be the direction of V and alpha? Sorry, omega and alpha. Okay, I'll tell you without wasting time. Now I'm going to draw this once again so that you can have a three-dimensional idea of this. So this is the circular path. Okay, so this is, assume the particle is moving like this. So this is the instantaneous velocity. We always, or we sometimes call it the instantaneous velocity, or we always sometimes call it tangential velocity. Okay, we can also call it tangential velocity. It was somewhere there in the note. Okay, so if somebody says what the tangential velocity is, that's the linear velocity at a particular time. Okay, so this is V, and take your, now the particle is moving in anti-clockwise direction, in the opposite direction of a clock. So now take your right hand, and keep your four fingers in the direction of the motion of the particle. And where would your thumb move? Your thumb is moving up. So that means that is the direction of omega and alpha. Okay? So, so even though the particle is moving in a circular manner, you can understand its direction is always changing at every second, every moment. So there should be one direction for that to be a vector. So that's how we find it. We keep in the right hand. You can even draw it using you can draw it like this, then you won't forget. Okay, Siddhant? Okay, I don't know. Okay, I hope I'm correct. Okay, so if this was moving the other way, in the clockwise direction, what would that be?
Down.
Yeah, it would go down. Okay, so alpha or omega is in the opposite direction. Please make a note of it, because I don't think that it was in the note. Okay, so in the next table you see the relationships, what I was talking to you about. Alright, let's do the first sum. Let's go to, a record spins on a phonograph at 33 revolutions per minute. Alright, before I do that sum, I need to give you some more equations. Alright, I'm not going to derive them, but when you do the sums, you need to have the knowledge of it. Capital T, what is denoted by capital T? Period of rotation. Capital T is a time, but it is always a period. What do you mean by period? Period means period for one rotation or one revolution or one oscillation. You know what an oscillation is? Oscillation, yes. So if something is happening in the same manner over and over, we call it,
Like a pendulum?
yeah, that's right. Like a pendulum, we call it an oscillation. So the time taken for one cycle is called the period. So this is T. T equals always 2 phi over omega. So I will quickly explain how we got 2 phi over omega. So T is one full circle, and in terms of pi, what is the angle that a particle would sweep? It should be 360 means 2 pi. Do you understand that? 360 means 2 pi. So over, what is the velocity? Velocity is the angular velocity, is omega. So T equals 2 phi over omega, and T is also can be represented as 1 over F. I hope you know this. Do you know this? F is the frequency. And then there was another equation which actually you can get from this. Omega equals 2 phi n, or omega equals 2 phi f. There is a certain reason for me to write n and f. The reason is, actually n is called the okay, so why don't you write this and block this out, and when we do the first sum, you will understand why I wrote two equations as n and f. Okay, but it's the same. Read the sum. A record spins on a phonograph at 33 revolutions per minute clockwise. Have you heard about RPM? Yeah. What does RPM mean?
Rotation.
Rounds or rotations per minute. So that's what comes here. So what is frequency? Number of vibrations per second. But in most sums, this particular parameter or the variable is given in terms of RPM. So always make it a point to convert the RPM into RPS, because there is no such term called RPS. It's RPM. All right. So this revolutions per minute is RPM. So both of them is actually the same. So these are revolutions per second. It should be. All right. So omega, for that sum they are asking for the angular velocity of the record. Omega equals 2 pi n. So 2 pi is already there. Now we have 33 revolutions per second, and you need to convert it into seconds. Rounds per minute. When you say per minute, this should go down. That means it is like 33 divided by 1 minute. And now this 1 minute has to be converted into seconds. Then that means it becomes 60. Alright, so this becomes pi 33 over 30 into pi. Okay? So you can do the simplification at home. And what should be the units of omega b? Radians per second. Okay? Radians per second. Alright. Okay. Estimate the magnitude of the Earth's angular velocity around its axis. So what should that be? Which equation should you make use of? I have given you. So they have not given us any data. We don't have anything. But we know everything.
The first one?
Yes, that's right. So what should it be?
Since it's just like a circle.
Yes, circle. So you say you are making use of t equals 2 pi over omega, and actually what we want is omega. So it should be 2 pi over t. So what we don't have any data there. What should it be? What should t be?
We just solve for.
Estimate the magnitude of Earth's angular velocity around its axis. So what is 2 pi means? One circle, one revolution. So what is the time it takes to move one revolution around its axis? Around its axis. 1 day. Do you understand? 1 day. So 2 pi equals 1 day, and what does 1 day means in seconds? 1 day has 24 hours, and each hour has 60 into times 60 seconds. And when you simplify that, you can get the answer. Okay? You understand? Alright. So, you can do, okay, I will do the next one too. I will do the next one, and you can do the fourth sum. So we already did 2 sums. I will do the third one, and you can do the fourth one at home. A frog rides a unicycle. If the unicycle wheel begins at rest, okay, please make a note of those. Its initial angular velocity is 0 and accelerates uniformly in a counterclockwise direction to an angular velocity of, now what should it be? 15 RPM. So it's not in rad per second. So please make it a point that we need to convert omega, the given value for omega, into rad per second. Okay, so keeping that in mind, let's move further. It says that this is happening within a time period of 6 seconds. Find the angular acceleration of the unicycle wheel. Okay, we have omega and we have time, and we are supposed to find the angular acceleration. So what is the angular acceleration? Angular acceleration is alpha equal, it's the rate of change of angular velocity, delta omega over delta t. So it's actually, it should be 15 here, and delta t should be 6. But I told you it's not 15 straight away because it's given in RPM. So you should convert it using what?
60.
No. Omega equals 2 pi n. Okay? So please make it a point to multiply it by 2 pi when an angular velocity is expressed in terms of an RPM. Okay? So you can even block this. So omega will be 2 pi n. 2 pi n would be 15, but still it's in RPM, therefore you need to divide it by 6. Did you understand that? So I will write that 60 here, so I think that is not confusing. So it's just a matter of simplification. So it's 2 pi 15, 6 into 60, 15 into 1, this is 4. So this is 3, and this will be pi over 12. And what should the unit be? Rad per square seconds. Okay? Please remember, rad per square second. So the next sum, you can do it at home. So I'm moving forward. The second objective for today is explain the acceleration and forces of an object moving in a circle at constant speed. Okay. Before I come to that. All right. In angular or rotational motion, okay, once again, I'm repeating this so that you will not get confused. In a rectilinear motion, we have velocity, acceleration. Okay. Then in circular motion, we have angular displacement. I forgot to tell displacement for the rectilinear motion. So you have this angular displacement, you have angular velocity, you have angular acceleration. And you know, so I will draw a circular motion. This is the linear velocity, it should be tangential. Then this is the displacement S and A, acceleration. Then this is theta, and this will be omega and alpha. In addition to these velocities and accelerations that we talked of so far, there is another acceleration that the circular objects, the objects which are under circular motion are subjected to. That's called centripetal acceleration, or it's always, or sometimes it is also known as aerial acceleration. Have you heard of that before? Okay, so to show how you get the aerial acceleration is a very complicated scenario, so I'm not going to do that. All what I want you to know is that there is, for any circular path, for any object which is moving on a circular path, has an acceleration towards the center, and that is known as centripetal acceleration. Okay? AC is known as centripetal acceleration. It's towards the center. That is what is meant by centripetal. Alright? So, and remember, this is not rotational. This is not angular. This is linear. It is always, when the particle is here, it is radial. I think I said a wrong word. It's not aerial, it's radial. It should be radial. It is always radially towards the center. Okay? Right. Now once again, what are the velocities you have? You have the rectilinear displacement, velocity, acceleration. Then you have the angular displacement, angular velocity, and angular acceleration. In addition to that, you have another acceleration which is called the centripetal acceleration, which is not angular. Please make it a point. So put a star and write, this is linear, not angular. This is a place that most kids confuse themselves. We are talking of a linear acceleration, now we are talking about an angular acceleration, now once again we are talking about a centripetal acceleration. What is this? Okay, so please make it a point. There are three sets: linear, angular, and centripetal towards the center. Okay, so they are right. So this centripetal acceleration is represented by v squared over r. We are not going to talk of how we got this. We are not going to talk about it at this stage. So AC equals v squared over a, v squared over r. And according to Newton's second law, which I was talking about with you last time, we know that F equals ma. Right? So when there is an acceleration towards the center, what does that mean, Siddhant? When something has an acceleration towards some place, what does that mean? It is being subjected to a certain force. That means there is a net force acting in that direction. So whatever that net force, according to Newton's second law, is called centripetal force. Okay? Now don't ask me what centripetal force is, I'm going to talk about it next. Okay? So whatever the force which is denoting an acceleration to the particle towards the interior is called the centripetal force. And this force is thereby represented by mv squared over r. You understand? Okay, so you can, I hope it's in the note. Yes, it is in the note. Alright, and you can block it out. Alright. Now, let's take a particle. Particles have, suppose you have a certain particle which is being hung. Okay? So, what are the forces acting on this?
Gravity.
The gravity. When it is being pulled by gravity, what do you call it? The weight. So weight is acting on it, and it is being pulled up by the string, causing a tension in the string. Okay. You understand? So these are the two forces. All right. Then, when a certain particle is kept on a certain floor, on a certain surface, what are the forces acting on this?
Weight.
Gravity. Weight is gravity, the force due to gravity. And what else? You put your hand on your other palm and try to feel what you feel from the other hand.
Friction.
Yeah, it's not friction. It's not friction. You feel something from your other hand. That is called reaction. Okay, so whatever we put on a certain surface, when we put something on a surface, everything is being subjected to a reaction from the other surface. Okay, so that is actually usually perpendicular to R. And since these are in equilibrium, R is equals to mg. Okay, so we are talking about weight, we talked about tension, we talked about reaction. So those are the kinds of forces that can act on objects. So what is this centripetal force? So it is not a new force. It is a part of existing forces. I'll show you how. Right. Let's consider a pendulum. This pendulum is moving in a circular path. Not the same way that it oscillates like this. It's moving in a circular path. Alright. Now tell me what the forces acting on this are.
The tension.
Tension, good.
And weight.
And the weight. Can you think of anything else? No. It's not even subjected to friction. It may be subjected to air friction, but we always assume that they are neglected. Okay? So this is tension and this is mg. Alright. Now, still this has the linear component of the velocity, the angular component of the velocity, linear acceleration, angular acceleration, as well as the centripetal acceleration. And it is subjected to the centripetal force. So this centripetal force is given by, what do you think? By which? By an existing force. By T.
Oh,
Okay? So the force which is responsible for the centripetal acceleration is the tension. So whatever that centripetal acceleration is equals to T if this angle is theta cos theta. Do you understand that? Okay, I'll show you another, because I'm explaining this a lot because this is a place where most kids confuse themselves. So this is not a pseudo force. This is a real existing force which is being produced by other existing forces. Okay, let's consider a cyclist who's taking a circular, who's taking a bend. Okay, so I cannot draw well. So what do you think the forces acting on the cyclist are? His weight and
friction.
the reaction or friction too, but in this case friction does not come because it's perpendicular. Okay, let's forget about the friction.
Okay.
Friction too has a component, but not here. Let's forget about it for the moment. There is a reaction acting from the road on the cyclist. Cyclist is on the road, so your feet can feel something that is coming from the flow. So that's the reaction, and it is at an angle. So now the centripetal force is given by the reaction r cos theta. Do you understand now? Do you understand how the centripetal force is coming up? Okay, so right, now go to the next figure. A diagram shows the top view of a 65 kg student at point A on an amusement park ride. The ride spins the student in a horizontal circle of radius 2.5 meters. Okay, not before, I'm sorry. This is the sum. In the diagram below, a car travels clockwise at constant speed in a horizontal circle. The figure is on the other side. Okay? At the position shown, which arrow indicates the direction of the centripetal acceleration of the car? Which arrow? There are 4 arrows. That's right, yeah, circle it. Okay, next one. The diagram shows the top view of a 65 kg student at a point A on an amusement park. The ride spins the student in a horizontal circle of radius 2.5 meters. Draw a vector on the diagram representing the direction of the centripetal acceleration of the student. Here, can you show me the centripetal? Do you have that figure? Yes, yes. Can you show me the centripetal acceleration? It's toward, that's right. So draw a line, and vector has a direction. So yes, you usually mark it as like this. Okay?
Oh, okay.
Yeah, so write AC. Yeah. AC. Do you get it? Did you get it?
Mhm.
Yeah, okay, let's go to the next one. A 0.5 kg object moves in a horizontal circular path with a radius of 0.25 meters at constant speed of 4 ms minus 1. What is the magnitude of the object's centripetal acceleration? Okay, so now I know, since I have been doing this for a long time, I know the equation straight away. Okay, so I will give you the equation. AC, they are asking about the centripetal acceleration. It is AC equals V squared over R. Alright, so what do you have? You have the constant speed. You have the constant speed. It's not the angular speed, Siddhant. It's the speed. So it's V. So V is how much? 4. Did you get it? 4 into 4 over, how much is R, the radius? 0.25. So this is 4 into 4 and 0.25 is also quarter. So I'm going to, yes, use 4 here as well. 64. Please remember the units are ms minus 1. It's not rad per second, square seconds. Please make it a point. Okay, so I hope you are not confused by this time. Alright, so what is the okay, so we found AC. So, and next one, 800 800 Newton running back turns a corner in a circular path of radius 1 meter at a velocity of 8 ms minus 1. Find the running back's mass, centripetal acceleration, centripetal force. What is the mass?
800.
That's in Newton. So what should the mass be?
We just divided
By what?
10.
10, that's right. So how much is the mass?
80.
80. So we write mass is 80. Okay? Alright, so what is the centripetal acceleration? Once again, go back to the equation. AC equals V squared over R.
So 64 divided by 1.
That's right. 64 ms minus 2. And they ask for the centripetal force. What should you do? Centripetal force is F equals ma, mass into acceleration. So now you have the acceleration with you to multiply it by n. Did you get it?
Yeah, so 8 times.
It should be
8 times 80.
yes, 80 times 64. Mass is 80.
Oh, yeah, 80 times 64.
Okay, so you write it should be 5,120. What should be the unit? Force.
MS.
Force is Newton.
Oh, yeah.
Yeah.
This is force.
Okay. Yeah, so make it as force. Write F. Yeah, it should be.
CF.
Yeah, so you write it F. CF. Okay, never mind. Okay, so the next sum and the next should be done by you at home.
Okay.
Miranda drives her car clockwise. Alright, this one I will do. Miranda drives her car, it's not difficult. Miranda drives her car clockwise around a circular track of radius 30 meters. She completes 10 laps within 2 minutes. Find Miranda's total distance traveled, average speed and centripetal acceleration. Right. Now you can do this sum in 2 ways. Even if you do whatever the way it is, both answers are correct. Right. Now this is a circular motion, but they are asking total distance, average speed and all the linear terms. They are asking for all the linear terms. So what is the total distance? What should be the total distance? 10 laps. You are running 10 laps. So how much should it be if you know the radius? 10 into
30.
10 into circumference.
Oh, 2 pi r.
Yes. So the total distance is 10 into 2 pi r. So it's
600 pi.
2 pi. How much is r?
30.
30. Yes, it should be 600,200, shouldn't it be? Isn't it?
No, it should be
60. This is 60. Yes, I'm sorry. 600 pi. Okay, that's the total distance. So what's the unit? We are talking about distance. So it's not
Meters.
angles. It's meters. Okay, it's not radians. Remember, please be careful. That's why this is an easy sum, but for the confusion only I'm doing this sum. Now average speed. So average speed is equals to distance over time. So what is the total distance? 600 pi. And what is the time? 2 minutes. What does 2 minutes means? Can you write 2 minutes?
120
No,
seconds.
120. So it should be something, it should be 5 pi
Yeah, 5.
ms minus 1. Okay, right. Now I'm going to do this. I'm going to take 1 minute and I'm going to do this in terms of angular velocity. Okay, so t, period of time period is t. T is how much? T is time for one oscillation is
2 minutes.
so total time had been 120.
So 1 lap every 5 minutes.
divided by 10, it should be 12 seconds. Okay, time for one. Then omega equals 2 pi over t. So 2 pi, t is 12. So you get 1 over 6, pi over 6. That's omega. But what do we want? We want v. So v equals r omega. V equals r omega. We didn't take a break. We want a break?
Can I just go get water really quickly?
Okay, I'll finish this up.
Okay.
V equals r. How much is r? R
25.
is
30.
30. Omega is pi over 6. Okay, so 5.
5 pi.
Okay, yeah. And I will finish the centripetal acceleration as well. Right? AC equals v squared over r. So v squared is this 5 pi squared over r. What is r?
30.
30.
So 5.
Yes, so 25. 5 squared over 30, that means 5 over 6 pi squared. Okay, okay, Sita. So whenever you want a break, please let me know. Okay? Yeah, go so. Now, we talked about equations of motions when on the first day in terms of translational motion. So there are actually 4 equations of motions that we talk about, but there are only 3 that we will be talking about here. So since you were not here, I'm going to brief you out about these 3 and you should know them by heart. Okay? So if here is a certain object whose initial velocity is u, which travels a certain distance s within a time t and acquires a certain velocity v by an acceleration a, okay, then v squared equals u squared plus 2as. You should know this by heart. Okay?
Do you have it somewhere?
Yeah, it's there. It's right here. Sorry, it's given in the paper. Okay? S, the displacement is equals to ut plus half at squared. V equals u plus at. So when you start your work in school, you will not be doing the same speed that we do. You will obviously remember this by the end of that particular section. Don't worry. Okay. Similarly, you can write the same equations for rotational motion. Suppose the initial angular velocity is omega 0, omega O original, which is going to be omega in a time t upon a displacement of theta and by an acceleration of alpha. Okay? You can write the same thing. You can replace. It's just a matter of replacement of variables. So v squared will be omega squared equals omega naught squared plus 2 alpha theta. Then s equals t theta equals omega naught t plus half alpha t squared. Omega equals omega naught plus alpha t. Alright? Even today, I can't write these by heart. What I do is, I write these 3 and then quickly replace the omega terms.
Okay.
Because they're quite confusing.
Yeah.
Right?
Yeah.
So, that's how you should also be. If you know these 3, you can always write that one. It's just a matter of replacement of variables. Alright. So, in the next section, we will be using these equations. Right. Now, do you understand the 3 equations, the uses of it? Alright. Let's do the first sum. A carpenter cuts a piece of wood with a circular saw. The saw blade accelerates. Okay. While I'm reading the sum, I will write the relevant particles. So in these sum siddhant, what we usually do is we write omega naught, omega, theta, alpha. What else? What else do we have? What did we miss? And time. These are the 5 variables that will vary all the time. Okay, in these sums, always write these set aside. Okay, then you won't miss anything.
So here they use A for X basically?
A for?
X. They don't use X here.
Yes. Okay, so I'll make it X. Okay, if it's confusing for you. We usually use it as X, S, but it can be also taken as X too. No harm. Okay? So, a carpet, okay, the first sentence out. The saw blade accelerates from rest. So, omega 0, O is 0. With an angular acceleration of 40 rad per square seconds. So, you don't even have to write the units. You just write the number. To its maximum speed of 14,000 RPM. So, please remember the angular velocity is now in RPM and it has to be converted. Okay, put a star there. It has to be converted. Don't use it straight away. Okay, so quickly at a side. Okay, before, I think it's one of the questions. It's one of the questions, yeah. Calculate the maximum speed in rad per seconds. What should you do? What should you do? How do you convert RPM into omega?
By 60.
No. Omega equals 2 pi
Oh,
n.
2 pi n, yeah.
Remember that, remember that. I'm circling that. Omega equals 2 pi n. So omega is 2 pi n is 14,000 and that is in rounds per minute. Therefore, it has to be divided by 60. So you will get this one as 14,000. No, 1400 divided by 3 pi. Okay, let's simplify it later. Let's keep it as it is. Okay, you can simplify that later. Did you get it?
No, it isn't. It's like 46.22.
Yeah, okay, what is this? Alright. Okay, the second question. How long does it take for the saw to reach its maximum speed? So what are they asking for? Okay, now look at this, Siddhant. You have omega O, you have omega, you don't have theta, you have alpha, you have theta. So you have 5 parameters and you have 3 equations and on 3 of them are known and you need to find 2. So you have plenty of data and plenty of equations which you can make use of. Alright, now what should you do? What should you find? You should find omega. No. Time. You have to find t. Can you tell me which equation to be used? Which?
Last one?
Last one, great, good. So you got it. Omega equals omega naught plus alpha t. So what I always tell my students is to write these equations before you start doing the sum. Then you don't need to spend time on thinking as to what equation we should use to. So omega naught equals 0, alpha equals 14 and time equals t. This is 14 pi over 3. So this 14 gets cancelled to this 14. This will be 100 pi over 3. Okay. Alright. And how many, okay, next one. How many complete rotations does the saw make while accelerating to its maximum speed? How many rotations? How do you find that? How many rotations? 1, 2, 3, 4. So if you know the displacement, total number of displacement,
Theta
and
this squared equals like 2a.
yeah, okay. First of all, think what to do. They are asking the number of revolutions. So if you know the total distance and if you divide it by the circumference of one rotation, you get the number of rotations, don't you?
Yeah, okay.
Okay, so let's find the total displacement. Which equation should you use? Now you are going to find theta. Which equation should you make use of?
The first one?
First one, yeah, let's make use of first one. Omega squared equals omega naught squared plus 2 alpha theta. So omega, this is 0. Omega squared equals 14 pi and this is equals to plus 2. Alpha is already known, that's 40, yes,
28.
and theta. Alright, so 1400 pi over 3 squared, you get 2 over 40 equals theta. Okay, let's simplify this a little bit more. So you have 2 1400s, you have pi squared, you have 9 here, you have 2 and 14 here, then you will get 14.
72.
Okay, so it will be 14 into 40, no, 14, 1, 2, 3, 4.
700 divided by
Yes. Divided by 18 pi squared. So you can simplify it. Alright? You can see that's theta. Now, what should be the number of
Rotation.
rotations?
Yeah,
Should
divided
be
by 2
equals
pi.
to theta divided by 2 pi r. So this pi, 1 pi would get cancelled. So theta equals, what is 2? What is r? How much is r? Isn't r given?
No, it's not good.
It's not given. Okay, so it should be given actually. So without that we can't do that. Okay, let's leave it as it is. Okay,
Okay.
switch. It is a small error because without that, oh no, you don't need theta, do you? Theta is the, I'm sorry, theta is the angle. So it should be divided by 2 pi. You don't need r.
Oh, okay. So
Okay.
just divide by
By 2 pi.
260
Okay.
degrees.
Got it? So have you completed writing?
Yeah.
Alright. Alright, so the next is up to you. Now in the second part of it, it is talking about a safety mechanism will bring the saw blade to rest in 0.3 seconds should the carpenter's hand come off the saw control. What angular acceleration does this require? So same thing in the opposite direction now. Okay, it should be done at home. Please do it at home, and we will see whether how far you have done. All right. Now let's go to the next part. Okay, utilize the definition of torque and Newton's second law for rotational motion to solve static equilibrium problems. Okay, we have 25 minutes. We can do some more. All right. What is torque? Torque.
I've heard it, but I never actually.
Yes, torque is actually a term which comes in rotational motion. Okay, which comes in rotational motion. In linear motion is the forces that we are dealing with. In rotational motion, the torque which is moving the circular disc or the circular object, whatever it is. Okay, suppose there is something hinged here, and it is being pulled by a certain force. But though it is being pulled by a certain force, it is linear. But what is actually rotating this is the torque. All right. So you can write torque is the turning or twisting force.
Okay.
Turning or the twisting force. It is a measure of force. A measure of a force tendency to produce tension. Produce torsion. I can't read you on my handwriting. A measure of.
What is force tendency?
It should be free. I don't know what I have written. Measure of. Okay, cut it. Measure of tendency to produce a torsion or a rotation. It's a measure of the tendency to produce a torsion or a rotation about a certain axis. Okay? It is a measure of the tendency to produce torsion or rotation about an axis. Okay. So simply, in linear motion, what is moving a certain object? A force. In rotational motion, the responsible party for the motion of a certain particle in a circular path is the torque. Okay, so you will see now V has a certain relationship with omega. V equals R omega. This too has a similar relationship. Alright, so torque. Let's consider a certain object, a certain rod, something like this, which is hinged here. Alright, and it is being pulled by a force F horizontally, so that it is taking a circular path. Alright, and this distance is R. So the force is moving it, but force is linear. It is linear at a certain time, and it is changing its direction all the time. So the torque responsible for this is given by R F. F R. So once again I am emphasizing S equals R theta, V equals R omega, A equals R alpha. Torque is denoted by this Greek letter tau. T-A-W. Some people call it tau. Some people call it tau. Whatever it is, I don't know what the correct word is. Only the Greek would know. So tau, can you see the relationship? Tau equals R F. Do you see this relationship? It's always R into the other one, the angular component. Tau equals A equals R F. No. F into R equals, so no, it's the opposite, isn't it? S equals R, V equals R R, F equals, yeah. So it's here is the opposite, here is the opposite, okay? So torque is force into displacement. It's not the displacement that we talked about when we were describing work. Torque is force into the perpendicular distance from the axis of rotation to the point of application. Did you get it? Tau equals force into the perpendicular distance from the axis of rotation to the point of application of the force. Alright? So this is the common word. Let's take an angled situation, like I'll read it here, like this, so that there will be an angle between this, theta. There will be an angle with this. And still this is rotating. And this is R. Now once again, tau equals F into R. So R is the perpendicular distance. So what is the perpendicular distance? Let me draw this nicely. This is extremely important. This is the angle. This is F. The perpendicular distance between the force and the axis of rotation is this. Do you understand that?
It's like Pythagorean theorem almost?
Yes. All what I want you to know is how to find the perpendicular distance. So if you are confused, draw a line across F, along X, not across, along F, and see what is the shortest distance from the axis of rotation. This is obviously not the shortest. This is obviously not the shortest. This is the shortest. Do you understand that? Yeah? Okay, so F equals, now this is theta. Therefore, this is also theta. Then how can you So F equals X. How can you represent X using R? How do you represent X using R? It should be R
squared equals
R
X squared.
sine theta.
Oh.
R cos theta is this side.
Okay.
Then the opposite is R sine
Sine
theta. Okay, so R sine theta. Therefore, the common equation for tau is equals to tau equals FR sine theta. Okay, that's given in the text. Yes. So, what are the units for this quantity? Are there other quantities with these units? Is it a vector? If so, which direction does the arrow point? The units of this quantity are once again Newton meters. You write Newton meters. Are there other quantities with these units? Of course. What are they? Work, energy. But they are not equivalent. Work is equivalent to energy. Energy is equivalent to work. They are almost the same, but not the torque. Even though they have the same units, they are not the same. Put a star and write it as it is. Torque and work are not the same, though they have the same units. So is torque a vector?
Yes.
Yes. If so, which direction does the arrow point? Once again, use the same rule. This is moving like this in an anti-clockwise manner. Put your right hand, take your right hand.
Doesn't it go like
Yes,
right?
goes up. Yeah, that's right. So according to this figure, the torque is upwards. This is the direction of the torque. And if it was moving the other way, what was it? This way. It would come
Down.
down. Do you understand that?
Just like the other.
Yeah, that's right. So omega, alpha, now tau are all in the same direction. Got it? Okay. Alright, so I'll do the next sum. A ship captain takes the helm and turns the wheel of his ship by applying a force of 20 newtons to a wheel spoke. If he applies the force at a radius of 2.2 meters at an angle of 80 degrees to the line of action, what torque does he apply to the wheel? So it's simply a matter of substitution. Tau equals F R sine theta. So F would be 20, R is 0.2 and sine 80. Okay, let's leave it as it is. Okay, so next one.
You're at home.
Yeah, do it at home. Okay, so right. Leave the next one.
Don't do it?
Yeah, the figure. Because I need to talk about, put a big star for this. I will come back to it when I do the next lesson. Okay, next part. Yeah, now I'm going to the next sum. Yeah, this one. Read it.
3 kg cafe sink
Is hung
is hung from a 1 kg horizontal pole as shown in the diagram. The wire is attached to prevent the sink from falling. Find the tension in the wire.
Okay, so on the first day we talked about vectors and we talked about forces and we drew force diagrams and we also did resolutions. Now, do you know equilibrium?
Everything's balanced.
Yeah, the balances. Do you have an idea of the
Yeah.
balances? So, do you know that if a certain system is subjected to a set of forces, its components in two perpendicular directions, and if the system is in equilibrium, the two components of the forces in two perpendicular directions is equals to 0. Do you know that? Okay, like this. Okay. Never mind. Let's take a little bit of time to do this because we did this before. Suppose there are, you have F1 and you have F2 and you have F3 like this. This is of course not linear. This will move this way. So I'll take it as something like this, F3, right? And if this angle is theta 1 and if this angle is theta 2, okay? If you take resolutions in this direction, it will be, you get F1, okay? Then you will get, what about F2? Would you get F2 straight away? No, you should get the horizontal component of it. So it should be plus, because since I took it in the forward direction, the resolution of F2 should be plus. So F2 cos theta 1. Then what should this be? Close this in this direction. F3 sine theta 2. What should it be its sign? Negative.
Oh, okay, this one.
Yeah, because it's in the other direction. When you close it, it's in the other direction. Do you understand that? So it should be F3 sine, you were right, theta 3 equals 0. If this is in equilibrium, if in equilibrium, alright? Similarly, let's take the other direction. Why I always take the horizontal and the vertical directions is because it's easy. It's extremely easy when you take those two. Alright, now what do you do here? Do you get F1? Do you get F1? No. Do you get F2? Yes. So it should be F2 sine, that's right, you're right, sine theta 1. Do you get F3? Yes.
Oh, yeah,
you can close it this way.
Yeah,
and what should it be? What should be the sign?
Plus.
Negative. The sign of it should be negative because I have selected the upwards, the upward direction. But it's closing downwards, therefore it's negative.
Okay.
Negative F3 sine, it should be cos, isn't it? Cos theta 2 equals 0. Okay. Now using this concept, we'll be doing the next sum. Alright? So this is the scene, and this is how it is hung. This is the string, okay. And this is the weight. There is a weight hung at 3 meters. This is 1 meter. 3 kg, right? Right. Now tell me the forces acting on this. Weight 30 Newton. What else do you think? Tension. This is being pulled up by the string. Tension. You have T. Right. Now Siddhant, you have 2 forces. Do you think that this would be in equilibrium if you have 2 forces? No. You need a third one too. Where do you think that the third one would come from? It is coming from here. It is coming from the place that this rod is hinged to the wall. And we call it the reaction. And if it is in equilibrium, Siddhant, please remember the 3 forces should cross one another. Actually, this R is not needed for the sum, but I am giving you the concept behind this.
Okay.
Do you understand that? Alright. So they cross one another. So now what I am going to do is, I am going to okay, I have to teach you another one too. I'm going to what do you call it, moment. Do you know how to take moment of forces? Okay, another one. Okay, moment. Okay, so you may think why I did not take the resolutions of forces. If I take the resolutions of forces Siddhant, I'm getting R2, which I have no clue of. It's making things complicated.
Okay.
So we have another way to do this. We call it taking moments. So taking moments is similar to taking torques. Moment is a force into perpendicular distance, similar to torque. Alright. So what we do is, we are going to take moment from A, and this is how we do it, A. Right? Listen carefully. Why I selected A? Why did I select A? There is a reason for me to select A. When I select a point, the moment of the forces about this point is 0. Therefore, I am not getting R. That's why I took A. Understand? Alright. So, moment is how this is being pulled by. If this is being rotated at, if this system is being rotated at A, how this 30 Newton force is being pulled by around A. Do you understand what I mean? That's the moment. Alright. So I can decide on a direction, either clockwise or anti-clockwise. So I'm taking an anti-clockwise direction. Now pull 30 Newton towards A. Pull 30 Newton towards A. What would it be? It will be in the same direction as the direction I took. So it should be in the positive direction. Okay? So 30, so moment is, I told you, force into the perpendicular direction, the distance. The force is 30, and what is the perpendicular distance? What is the perpendicular distance?
4.
3. Not 2. 4 is up to here.
Okay. Oh, yeah.
This square is hung at 3.
Yeah.
So 30 into 3. Got it? Now take T. Pull it towards A. Pull it towards A. What would be the direction? Would it be clockwise or anti-clockwise? Pull it towards A.
Anti-clockwise?
Yeah.
So
it should be negative. You're right. T equals T into, now the perpendicular distance. Now is a little bit confusing, Siddha. Because here we had the perpendicular distance from A to the object. But whereas for T, it is slanted and it doesn't have a perpendicular distance that we can see straight away. So let's see. What would be the perpendicular distance? This is the line of action, though it is being pulled at B. So this is the perpendicular direction. You understand? So this is what the distance should be. Alright, so if a system is in equilibrium, the addition of the moment of force, the algebraic sum of the moment of forces should be equals to 0. Okay, so this is equals to 0. Now what should be x? What should be x? This angle is 30. So this distance is 4.
Yes.
And therefore this angle is 60. So x is 4
So that'd be
cos 60.
30, 60, 90.
Do you understand?
Yeah.
So x equals 30, this is 90, t into 4 cos 60. So 90, 40, cos 60 is how much? Cos 60 is sin 30, that is half. So 0, so this should be 2, t will be 45 Newton. Okay, so using this sum, I taught you about resolution of forces. And I also talked to you about
Moment.
moment. You call it moment.
Okay.
Moment of, some people call it moment. It's moment, whatever it is. Moment of forces. Okay? So, these are the two important points. In an equilibrium system, the resolutions of forces in two perpendicular directions is equals to 0. In an equilibrium system, the moment of forces about a certain point is equals to 0. There are certain conditions, Siddhant. It's like, say, either 3 moments should be equals to 0. Or 2 equilibrium, 2 of these plus this should be equals to 0. Then only a system is in equilibrium. Though there are conditions, but for this case, you don't need to know more. Okay? So, it's almost 9. I will take another 5 minutes and talk to you. So you can, I'll talk to you about moment of inertia. Alright. I will talk to you about moment of inertia and stop. Okay. So what is moment of inertia? I know you don't know what moment of inertia is. What is mass? Mass is the matter, right? So it is actually, according to Newton's first law, mass is a measure of the reluctance of for motion, right? You have a heavy mass, you have a light mass. If you push the same thing, this would move soon. This move, because of the shape also, it would move fast. But this is much heavier. So mass is a measure of how reluctant it is to get subjected to a motion. Okay. So inertia too is a similar parameter in circular motion. So it's actually not mass straight away, but something related to mass. Measure of moment of inertia is how reluctant a mass is to move circularly. Alright? So this moment of inertia is expressed by a certain term. Go home and read this again. I equals mr squared. Right? So if this is the axis and if this is the object and if this is moving, the moment of inertia I equals the mass of the object into the distance. Okay? Let's assume a particle, right? So this is the distance r from the axis of rotation and this is the mass. So I equals mr squared. Alright? Yeah. So that will not be the same always, Siddha. That will not be the same always. Can you look at this? Right? I want you to only remember this. If an object is a particle, its moment of inertia is mr squared. If an object is a rod, it will be ml squared over 3. So you have to memorize this. So but don't worry, in school this is a long unit and you have ample of time to grab this into your head and master this. Okay? We are just giving you a basic idea. Okay. Alright? If it is a rod which is moving about an axis which goes through the rod, then I is a different scenario. I equals ml squared over 12. Okay. Right? Then you go to the next one. A circular hoop is mr squared over 2. Okay? And if it's a circular disc, a solid disc, mr squared over 2. And if it's a cylinder, I equals mr squared. Okay? So you have plenty of things which is written here. You can go home and read them. All what you should know, it was at I is I is analogous to mass in linear motion. It's like V to omega and A to alpha and tau to F
Okay.
and M to I. Okay?
Mhm.
It is a parameter which says how reluctant a mass is for a circular motion.
Okay.
Alright? So I'm going to stop here and we'll be actually these are actually not necessary. So this is how this is actually too much. For a disk having a hollow, this is a cylinder. Can you get an understand of? Can you understand the figure of this? This is the
Cylinder and there's a
eye
pin cut
of
in.
Yes. These are too much. This
Okay.
is just for your information. Okay. So this is how it would be for these. This is how it would be for a solid. Okay. So having that knowledge, I will be going back to this next time. Okay. I will be going back to this next time, that tau equals I alpha. Okay, I will tell you that too. F equals ma. So F is tau, m equals, I told you, I, moment of inertia, a equals alpha. F equals ma, tau equals I alpha. Okay, so next time I will start from there. Alright? Tau equals I alpha. So do the homework.
Okay. Wait, is there a homework sheet?
Yeah. Week 2. This is week 2 homework.
Okay.
Yeah, for the former work. For the homework.
Is
You
there
can do this one too.
3?
Yeah.
So do both?
Yeah, of course.
Okay.
In school you will get plenty, heaps and heaps of sums. Not one or two.
Okay.